Okay, so we're going to continue looking at how current electricity behaves. We're going to look more at electrical circuits that would occur in a home setting, for instance, or at least in a more practical use. So it's all about controlling the flow of electricity today. Here we go. So we're going to look at the ways, or the various ways, that electricity in a circuit can be controlled. We first really need to have a good understanding of resistance, so we're going to review that quickly. Resistance actually plays quite a significant role in what we're going to talk about today, so it's important to know what resistance is. We're going to talk about the difference between conductors and insulators and resistors. There is a difference, of course, between all three. We're going to talk about the purpose of resistors in appliances, so we're going to look at like a household kind of view of this today, and then we'll look at variable resistors, also called rheostats, and electrical switches. Shouldn't be too long of a day. Let's get going. All right, so recall from last week that we looked at three main characteristics of electricity. There was voltage, current, and resistance. So voltage is, of course, measured in volts. And the best way of thinking about voltage is it's just how much energy each particle has, or in other words, it's just how much push exists within that current. Now, the current itself is measured in amps or amperes, and it's actually how much flow of electricity there is, right? So it's like how much electricity is actually flowing through the whole system. Resistance, on the other hand, the one that we're really going to have to look at a bit today, is the ability of an object to oppose the flow of electricity. And it's measured in ohms, which is represented by that Greek symbol omega. Now, more resistance means it's harder for electricity to flow. So if you have a high resistance, it's going to be really, really tough for electricity to flow through that object, right? And sometimes you want to control the resistances for various purposes, and we'll see about that later. So again, we're going to focus more on resistance today rather than voltage or current. So resistance, an object that allows electricity to flow through it easily is called a conductor. That shouldn't be a big surprise to us. Things that conduct electricity are conductors. Now metals, of course, that's probably the easiest example of an excellent conductor. All metals conduct electricity. Some are better at conducting electricity than others, but they're all excellent conductors. Now an object that doesn't allow electricity to flow through it is called an insulator. Now, a really good example of an insulator, of course, would be rubber. Rubber is a really good insulator. Electricity does not flow through that very well. Now, however, there are some conductors that don't allow as much electricity through as other conductors, and in some applications, this is actually useful. Sometimes you would prefer not to have as much electricity flowing through a conductor as otherwise, right? So in other words, it's important sometimes to have a higher or lower resistance. Conductors that don't allow as much electricity to flow through are called resistors. Now, a resistor is not the same thing as an insulator, of course. It still allows a fair bit of electricity through. It just has a higher or lower resistance, usually a higher resistance if it's a resistor, let's be honest here, and that would control the current. Now, resistors with higher resistance, in other words, more ohms, are going to lower the current. In other words, when you increase your ohms, you're going to decrease your amps. That's the idea here. Now, we've talked about resistors before. This isn't totally new. You probably look at this picture and say, hey, that's the same one you used before. Yeah, I know, I'm being real original here. But we're going to focus in a little bit more on what resistors really do today. And again, it's important to understand electricity still flows through them. It's not that they're an insulator where electricity won't. It still lets electricity through. All right, so increased resistance causes the conductor to gain more energy from the electrons flowing through it. So that's what happens when you have more resistance, basically because it's having a hard time pushing the electricity through the whole current. The energy from that, so it's related to the volts, of course, the energy from that has to go somewhere. So the gained energy is often radiated as heat or light, right? So in other words, when you have something with a high resistance that's got electricity flowing through it, you might have heat that gets generated in that resistor. Now, some devices are produced to act as resistors because we actually want that heat or light. Some obvious examples would be a light bulb or even like an element on the stove, right? An element on the stove is a higher resistance than the current or than the wiring that would lead into it. That's why the element on the stove gets hot, but then the wires that are inside the stove don't, right? Because this is made of a different material with a higher resistance. Now, solutions as resistors. It doesn't have to be a solid that acts as a resistor. Usually when we look at resistors, we think of some sort of, some kind of metal or something. But solutions, so liquids, can act as resistors too. Now, it's often said that water is a good conductor of electricity. This is only partly or partially true, right? So in other words, when we say water is a good conductor of electricity, we just mean like water in the natural environment. So it could be from a lake, a river, or an ocean, or even just from your tap. That kind of water is a great conductor of electricity. In case you're not aware, the water that comes out of your tap or from a lake or a river or ocean isn't 100% pure water. There's minerals and stuff that's dissolved in it. Obviously, in very small quantities, it's not like gonna harm you or anything. Well, I mean, some lake, river water is gonna maybe harm you. That's why you got to boil it sometimes. Ocean water is not good for you. It's got tons of salt in it. That's an obvious one. But again, water from the tap or from a natural environment has things dissolved in it. And those things that are dissolved in it are often conductors themselves. And when they're dissolved in the water, they make the water act as a conductor. Now, completely pure water, so in other words, water that's got everything removed from it, we call this distilled water because it's literally made by distilling it. It's like by boiling it and condensing it, and it's a whole big process basically. But in other words, completely pure water with nothing dissolved in it is actually not a good conductor of electricity at all, right? Pure distilled water is really not a good conductor of electricity. And this is partially due to the fact that water molecules themselves are actually electrically neutral. There's more to it than that, of course. Water is, if you remember, a molecular compound rather than an ionic. And of course, when you have dissolved minerals and stuff in it, those can act as ions that float in it. And then, of course, that produces a way for electricity to flow, but that's more complicated. You don't need to know that. Anyway, a batch of distilled water can actually be checked for its purity by attempting to run an electric current through it. So in other words, when they make distilled water in a distilled water factory, they could test how pure it was by trying to run an electric current through it. And if electricity runs through it pretty easily, that would tell you it's not actually pure water. There must be some things dissolved in it. All right, so next up with resistors, there's a thing called a variable resistor. This little animated picture in the bottom right is kind of showing how it works. We'll get to that in a second. But for some applications, you actually want to change how much resistance and therefore how much current, because remember, as resistance goes up, current goes down, and vice versa. So in other words, sometimes you want to change how much resistance and therefore how much current passes through the conductor. So there's a thing called a variable resistor, and it's actually more commonly known as a rheostat. And these are used to control that. So it changes the resistance of the conductor, allowing varying currents to pass through. Now you might think, well, why do we care? Why would we want to change the resistance? Why would we want to change how much current's flowing through this? Well, rheostats are used for dimming lights. If you've ever seen like a dimming light switch, of course, when it's up at max, your light's really bright, but then you can lower it down and the light gets less and less bright. That's because the resistance is changing as you do that. You're actually upping the resistance and therefore lowering the current, which is therefore lowering the brightness of the light bulb. Same within in a stereo, when you change the volume on a stereo, this little knob thing here, when you're like spinning the knob, generally speaking, especially if it's like one of the ones that's done manually, like the older ones. The newer ones might be digital, it might work a little bit different, but the older ones, of course, what it would do is it would change the volume by actually affecting how much current's passing through the stereo. So in other words, it's limiting more or less how much power the stereo is actually getting from that. Now, in terms of this picture showing how it works, this is more like a sideways view of one of these ones, right? So if like you turn this sideways, and this is like the switch that you're pulling up and down. As you're moving the switch, what it's doing is it's basically using this little switch piece as a connection on a bunch of coils of wire, right? And as the wire coils around the central rod here, of course, that's actually going to be affecting the resistance, right? So it's either increasing or decreasing the resistance depending on how many times it had to coil over to get there, right? So that's how a rheostat would work. Anyway, moving on. Ooh, if it's going to let me. There we go. Switches. All right, this is actually the last thing we're going to talk about today. I told you guys it was going to be a really quick lesson. So lastly, a switch is a device that can start or stop an electric current. Yeah, I know, big shock, right? Like we're stunned by that. Okay, anyway, so the basic idea behind a switch is that a closed switch creates a complete circuit. So in other words, you close a switch off, that creates a complete circuit, whereas an open switch, so if you open the switch up, it creates an incomplete circuit. So remember, electricity only flows if the circuit is complete. So you need to have a closed switch for electricity to work. Some people sometimes find that backwards, because sometimes you think, oh, it's closed, nothing's going to work. No, it's backwards with electricity. A closed switch means electricity is flowing. An open switch means electricity is not. So again, this picture, by the looks of it at least, it looks like there's a closed switch here. It looks like there's a connection, but if you move this knob away, you wouldn't have a connection anymore. So you can notice it's going from one end of the battery through our load, which is a light bulb here, and then through the switch, and then back to the battery. So that's a complete circuit as a closed switch. But if you opened it, electricity wouldn't flow because the circuit is not complete. Now, if you look at it like a light switch, I found this picture online. It's kind of interesting. It's more complicated than I think I would have even imagined. I'll be totally honest with you, I've never taken apart a light switch before, so this was a bit of a surprise to me. But this is how it basically works. Just to break it down, you can pause and like really look at it if you need. The toggle on the light switch basically is connected to a spring which holds it in place. And as you move it up or down, there's two bumpers that will stop the light switch from just completely going off, right? So if you had a totally broken light switch, it might be because the bumpers are broken, and that would make this light switch kind of flimsy, right? Anyway, there's like a metal rod inside of here And when you have it in the off position, the toggle itself, so the actual like light switch piece that you're actually pushing, is actually pushing against this metal bar, which is pushing it away from the contact point and therefore closing the circuit. So when the light switch is down in the off position, this bar gets pushed in, which of course creates an incomplete or open circuit, right? So in other words, it's not going to have the electricity flow through the whole system. And in case you're wondering, hey, where's the electricity going through? This part I do know. When you hook up a light switch, there's usually a couple different ways of doing it, depending on the way your house was set up or whatever. But there's these screw terminals on the side, and usually the wiring inside the light outlet actually has the wires come out in like a hook, and you hook them around the screw terminals here, and then you screw them in so it holds it in place. So in other words, the circuit, of course, is only complete if this piece, which is connected to this contact point, and this piece, which is connected to this contact point, have a complete circuit running through. And that's the form of the switch, where the switch, if it pushes it in here, it breaks that circuit, and the electricity through that switch is no longer flowing, right? Because it's not a complete circuit. Anyway, I feel like I rambled about that for too long. It's just a light switch. That's about all you need to know. So we're done. Page 303, questions 1, 3, 7, and 9. Not even all that many questions. It's just, I guess, 5 questions for you to work on. Please get those done. Again, it was an easier day today. That's all well and good. But as always, if you have any questions from this, or if you're really stuck as to what a rheostat is, because I think that was the hardest thing we learned today, please let me know. Best of luck, guys.